Imagine this. The first human colonists have just landed on Mars. The spacecraft settles gently onto rust-coloured soil that has waited 4 billion years for this moment. Through the viewport, men and women gaze out at endless valleys carved by ancient rivers, mountains that dwarf Everest, and a sky painted in shades of salmon and copper. They have travelled 140 million miles across the cosmic ocean. They carry with them the hopes of an entire civilization, the accumulated dreams of every generation that ever looked up at that red wandering star and wondered, could we live there? This is humanity's greatest achievement, the beginning of our transformation from a single world species to an interplanetary one. Now imagine this. Just 8 months later, the same colony sits abandoned. Equipment lies scattered across the regolith like the bones of some great extinct creature. Habitats stand silent, their airlocks sealed against the thin Martian atmosphere, their corridors dark and cold. Inside, systems have failed, resources have been exhausted, and the colonists, those brave pioneers, have either perished or retreated to Earth, defeated not by lack of courage, but by the unforgiving mathematics of survival on an alien world. What happened in those 8 months? How could humanity's grandest dream collapse so completely, so quickly? Tonight we will journey not to Mars itself, but into the scientific reality that waits there, the brutal, uncompromising truth that lies hidden beneath every glossy animation and optimistic timeline. We will examine, system by system, failure by failure, exactly why a Mars colony would not simply struggle, but collapse within months of its founding. This is not a story of distant futures or theoretical problems. This is an analysis of the immediate concrete challenges that no amount of enthusiasm can overcome. The atmospheric conditions that make every breath a calculated gamble. The radiation that silently destroys cells with each passing hour. The food production systems that cannot possibly yield enough nutrition. The water extraction that demands more energy than any colony could generate. The cascade of dependencies where the failure of one system guarantees the failure of all the others. The public imagination has been captured by visions of thriving Martian cities, domed gardens beneath salmon skies, and humanity's triumphant expansion into the cosmos. But between the dream and reality lies a chasm wider than the Valles Marineris itself, filled with engineering challenges so profound, biological limitations so severe, and resource constraints so absolute that our current technology stands helpless before them. If you find yourself drawn to these journeys into hard science and uncomfortable truths, please consider liking this video and subscribing. It helps us continue exploring not just where humanity might go, but whether we truly can. And I'm curious, where are you watching from right now? What time is it where you are? Are you drifting off to sleep or perhaps just beginning your day? Leave a comment below. I love knowing that these cosmic explorations reach across time zones, connecting us all under the same sky, the same stars, even as we contemplate worlds so far away. Now settle in. Let your mind open to the reality that awaits 140 million miles from home. We will walk through the Martian day not as tourists, but as scientists, engineers, and realists. We will count the breaths in a failing life support system, measure the rads accumulating in human tissue, calculate the calories that cannot be grown, and witness the slow, inevitable unravelling of humanity's first interplanetary colony. The dream of Mars is beautiful, but dreams, no matter how beautiful, must eventually face the morning light of physics, chemistry, and biology. Let us begin. When we imagine standing on the surface of Mars, We often picture ourselves gazing up at the rust-coloured sky, feeling the crunch of ancient soil beneath our boots, marvelling at the alien horizon stretching endlessly before us. But we rarely consider the first biological truth of that moment. Every single breath would be impossible, not difficult, impossible. Mars does not simply offer thin air. It offers no air at all, not in any form that human lungs could recognize or use. The atmosphere that surrounds us on Earth, the invisible ocean we swim through every moment of our lives, simply does not exist on Mars. And this is not a problem that can be solved with ingenuity alone. It is a fundamental barrier that transforms every second of life on Mars into a battle against suffocation. The numbers tell a stark story. Mars possesses an atmospheric pressure of just 0.6% that of Earth. To comprehend what this means, imagine standing at an altitude of 100,000 feet above Earth's surface, more than 3 times higher than commercial jets fly, higher than the edge of space itself. At that altitude, the air is so thin that exposed human tissue begins to fail. Blood vessels rupture. Consciousness fades within seconds. This is the atmosphere of Mars, not at its highest peaks, but at its lowest valleys. Everywhere on the planet, the pressure is so low that it exists at the boundary between atmosphere and vacuum. It is not an environment that challenges human survival. It is an environment that forbids it. But pressure is only the beginning of the nightmare. The composition of Mars' atmosphere is perhaps even more hostile than its thinness. 95% of the Martian air is carbon dioxide, the very gas we exhale as waste, the molecule our bodies are designed to expel, not inhale. There is no oxygen to speak of, less than 0% by volume, far too little to sustain even a single breath. If a colonist suit were to rupture, if a habitat seal were to fail, suffocation would not take minutes. It would take seconds. The body would gasp reflexively, pulling in a lungful of carbon dioxide, and the brain would begin to shut down almost immediately. There would be no time for rescue, no opportunity for emergency protocol. Death would arrive with the speed and certainty of a light switch turning off. Yet the absence of breathable air is not the only atmospheric threat. The lack of pressure itself creates a phenomenon so horrifying it seems drawn from science fiction rather than science fact. At Mars's atmospheric pressure, the boiling point of water drops to just above freezing. This means that human bodily fluids, blood, saliva, the moisture in lungs, would begin to boil at room temperature. Exposed to the Martian atmosphere, a human body would not freeze first, though freezing would come soon after. It would bubble. Dissolved gases in the bloodstream would effervesce like a carbonated drink opened at altitude. This condition, known as ebulism, causes massive tissue damage within moments. The eyes would swell, the tongue would expand, consciousness would vanish in fewer than 15 seconds, and death would follow within 2 minutes. The atmospheric pressure on Mars is not simply insufficient. It is lethal in ways that challenge our deepest instincts about how the universe should work. Knowing this, any Mars colony must create its own atmosphere, a manufactured bubble of Earth-like air maintained constantly, flawlessly, without interruption. Oxygen generation becomes the single most critical system in the entire settlement. Most proposed designs rely on electrolysis, the process of splitting water molecules into hydrogen and oxygen using electrical current. In theory, this is elegant. In practice, it is an engineering nightmare that consumes staggering amounts of energy and requires components that wear out, corrode, and fail. On Earth, backup systems exist. Spare parts arrive within days. On Mars, there is no resupply. There is no backup. If the oxygen generation system fails, the colony has only the air that remains in its tanks and habitats. Hours, perhaps days if rationing is extreme. Then silence. The psychological weight of this reality cannot be overstated. Every colonist would wake each day knowing that a single malfunction, a single error in maintenance, a single undetected crack in a seal could mean the end of everything. The air they breathe would not be a given, but a product, manufactured and maintained by machines that must never stop working. Sleep would become a gamble. Would the oxygen scrubbers continue functioning through the night? Would the pressure regulators hold? There is no opening a window for fresh air. There is no stepping outside to catch your breath. The atmosphere is not around you. It is manufactured for you, and if that manufacturing stops, you die. Habitat leaks present another dimension of terror. On Earth, a crack in a wall is an inconvenience, a source of drafts or moisture. On Mars, it is a countdown to catastrophe. Atmospheric leaks would be almost impossible to detect quickly. The habitats would need to maintain positive pressure to prevent Martian dust and air from seeping inward, but this very pressure would drive breathable air outward through any breach. A pinhole leak might go unnoticed for days, slowly depleting oxygen reserves. A larger breach, caused by micrometeorite impact or structural fatigue, could depressurize a habitat in minutes. Alarms would sound. Seals would slam shut between modules. But if colonists were caught in the wrong section, there would be no time to don suits, no opportunity to reach safety. The air would simply vanish, and with it, life. Even assuming perfect seals and flawless oxygen generation, the colony must still contend with carbon dioxide. Every human exhales roughly 2 pounds of CO2 daily. In an enclosed habitat, this gas accumulates rapidly, and if not removed, it becomes toxic. Carbon dioxide scrubbing systems which chemically bind and remove the gas from breathable air are well-tested technology aboard spacecraft and submarines, but they fail regularly. On the International Space Station, with constant monitoring and immediate resupply capabilities, CO2 scrubbers have malfunctioned multiple times, requiring emergency repairs and backup systems. On Mars, there is no backup. If the scrubbers fail, carbon dioxide levels would rise steadily. First come headaches and fatigue, then confusion and impaired judgment, finally unconsciousness and death. The cruel irony is that colonists would not suffocate from lack of oxygen, but from poisoning by their own exhalations. They would drown in the air they breathed out. Maintaining these life support systems is not a matter of occasional upkeep. It is a relentless, daily battle. Filters must be cleaned or replaced. Chemical beds must be regenerated. Sensors must be calibrated. Every component is under constant stress, operating in conditions far harsher than anything experienced on Earth. And all of this occurs while colonists are already stretched thin, managing food production, water extraction, habitat repairs, and the 1,000 other tasks required to survive. The margin for error is non-existent. A forgotten maintenance check, a misread sensor, a delayed repair, any of these could cascade into catastrophe. Then there is the dust. Mars is a desert world, and its dust is unlike anything on Earth. Martian dust is fine, electrostatically charged and invasive. It clings to surfaces. It infiltrates seals. It finds its way into every crevice, every joint, every mechanism. On Earth, dust is an annoyance. On Mars, it is a systemic threat. Air filtration systems, already working overtime to maintain breathable atmosphere, would become clogged with dust within weeks despite the best engineering. Filters designed to last months would need replacement in days. The dust particles are also toxic, containing perchlorates that damage human tissue and disrupt biological systems. Breathing even trace amounts could cause long-term respiratory damage. The colony's air must not only be pressurized and oxygen-rich, it must be absolutely impossibly clean. Every technical challenge compounds the others. Oxygen generation requires water, but water must be extracted from Martian soil or ice, a process that itself demands energy and equipment prone to failure. Scrubbing carbon dioxide produces waste heat, which must be vented, but venting systems require moving parts that wear out. Maintaining pressure requires perfect seals, but seals degrade under temperature swings and radiation exposure. The atmospheric systems are not isolated problems. They are interconnected dependencies, each relying on the success of all the others. If any single system falters, the entire chain collapses. The colonists would live inside a paradox. They would inhabit a world with an atmosphere, yet they would be surrounded by airlessness. They would stand on the surface of a planet, yet they might as well be floating in the vacuum of deep space. The psychological toll of this reality is difficult to overestimate. On Earth, even in the most hostile environments, there is always air. A mountaineer at extreme altitude still breathes thin air. A sailor in a storm still draws breath from the wind. But on Mars, the atmosphere is not your ally. It is not even neutral. It is hostile, foreign, and utterly indifferent to human life. And so we return to the central truth. On Mars, every breath is not a gift. It is a manufactured product, created by machines, sustained by energy, dependent on flawless engineering and constant vigilance. There is no backup plan, no margin for error, no safety net. The atmosphere of Mars does not challenge human survival. It denies it. To live on Mars is to accept that the air you breathe exists only because you force it to. And the moment you stop forcing, the moment the machines falter or the seals crack or the systems fail, the atmosphere will reclaim what you have borrowed. And in that silence, in that thin and toxic air, the dream of a Mars colony would not collapse slowly. It would suffocate, gasping in the span of a few desperate breaths. This is not speculation. This is physics. This is biology. This is the atmospheric nightmare that every Mars colony must confront, not as a distant problem to be solved someday, but as an immediate, relentless, unforgiving reality that begins the moment the first colonist steps onto the red soil and tries, impossibly, to breathe. Beyond the thin atmosphere and the dust storms, beyond even the struggle for breathable air, lies a threat that is invisible, relentless, and inescapable. Radiation on Mars is not merely dangerous. It is a constant, silent assault on every living cell, every electronic system, every moment of existence. Unlike Earth, where magnetic fields and a thick atmosphere shield us from the violence of space, Mars stands naked before the cosmos. Its magnetosphere vanished billions of years ago, leaving the surface exposed to radiation levels so extreme that colonists would receive approximately 700 times more exposure than they would on Earth. This is not a challenge to be overcome with ingenuity or determination. This is physics, unrelenting and absolute. To understand the radiation crisis on Mars is to understand that we evolved under the protection of forces we barely notice. Earth's magnetic field wraps around our planet like an invisible shield, deflecting charged particles from the Sun and deflecting cosmic rays that traverse the galaxy. Our atmosphere absorbs what remains, scattering high-energy radiation before it reaches the ground. On Mars, these protections do not exist. The planet's magnetic field died when its core cooled, and its atmosphere thinned to 1% of Earth's density. What remains is a world laid bare, where every sunrise brings not warmth and light, but invisible particles travelling at nearly the speed of light, penetrating flesh, circuits, and steel with equal indifference. The radiation comes from two primary sources, each deadly in its own way. Solar radiation arrives in waves from our sun, mostly as charged particles carried by the solar wind. On Earth, we never feel this bombardment. On Mars, it is constant. But far more insidious are galactic cosmic rays, high-energy particles accelerated by distant supernova explosions, racing across the void for millions of years before striking Mars with undiminished force. These particles are not photons of light that can be blocked by simple barriers. They are atomic nuclei, hydrogen, helium, iron, travelling so fast that they pass through matter like ghosts through walls, and when they strike human tissue, they shatter DNA strands, damage cell membranes, and leave trails of ionized destruction in their wake. The numbers are staggering and unforgiving. A colonist living on the surface of Mars, even inside a habitat, would absorb roughly 200 to 300 millisieverts of radiation per year, compared to the 3 millisieverts an average person receives on Earth. This is not a gradual risk. It is a guarantee of cellular damage accumulating daily. Within months, the probability of developing cancer begins to climb. Within years, it becomes a certainty. Cognitive decline, cardiovascular disease, and immune system failure follow inevitably. Radiation does not negotiate. It does not wait for better technology or more research. It acts immediately and continuously, eroding the biological foundation of life with silent precision. And then there are solar flares. These eruptions of superheated plasma from the sun's surface can hurl billions of tons of charged particles into space in a matter of hours. On Earth, we watch them as beautiful auroras dancing across polar skies. On Mars, they are death arriving without mercy. A major solar flare could deliver a lethal dose of radiation to unshielded colonists in mere hours. The warning time would be minutes at best, the time it takes for sensors to detect the flare and for light to travel from the sun to Mars. In those precious minutes, colonists would need to retreat to heavily shielded safe rooms, abandoning whatever tasks they were performing wherever they were on the surface. Miss the warning, or be caught too far from shelter, and the consequences are not injury but mortality. Solar flares do not announce themselves with thunder or visible light. They arrive as invisible waves of death, and Mars offers no place to hide. Shielding against this radiation is not a matter of building thicker walls. The particles that comprise galactic cosmic rays are so energetic that they pass through aluminum, steel, and plastic, as if these materials barely exist. To meaningfully reduce radiation exposure, a habitat would need to be buried under several meters of Martian regolith, the rocky soil that covers the planet's surface. Water, with its hydrogen-rich molecules, is even more effective, but it would require surrounding habitats with tanks containing tons of liquid, a resource already desperately scarce. Every kilogram of shielding adds to the mass that must be transported from Earth or excavated and processed on Mars. The construction complexity multiplies exponentially. Building a habitat becomes an exercise in moving mountains of dirt, all while colonists themselves are exposed to lethal radiation during the construction process. It is a paradox with no elegant solution. Even if habitats are buried deep beneath the surface, the radiation does not simply vanish. When high-energy cosmic rays strike shielding materials, They interact with atomic nuclei and create secondary radiation, a cascade of particles that can be as dangerous as the original cosmic rays. This phenomenon, known as secondary radiation or spallation, means that some shielding materials can actually increase radiation exposure rather than reduce it. Aluminum, commonly used in spacecraft construction, is particularly problematic. When cosmic rays strike aluminum, they produce showers of secondary particles, including neutrons, which are exceptionally difficult to block and highly damaging to human tissue. Engineers face a grim calculation. Too little shielding, and colonists are exposed to primary radiation. Too much of the wrong material, and they're bombarded by secondary radiation instead. There is no perfect shield, only a range of inadequate compromises. The effects of chronic radiation exposure extend far beyond cancer risk. Studies of astronauts aboard the International Space Station, which orbits within Earth's protective magnetosphere and still experiences elevated radiation, reveal troubling patterns. Cognitive decline, memory impairment, and slower reaction times appear even after relatively short missions. On Mars, where radiation levels are orders of magnitude higher, these effects would accelerate. The brain is particularly vulnerable to cosmic rays. When high-energy particles strike neurons, they can cause inflammation, disrupt neural pathways, and damage the delicate structures that enable thought, memory, and decision-making. A colony depending on sharp minds for survival would slowly watch its members' cognitive abilities erode, decision-making deteriorate, and critical errors multiply. The radiation does not merely threaten life, it threatens the capacity to sustain a functional society. Electronics and computer systems face their own radiation crisis. Integrated circuits, memory chips, and processors are exquisitely sensitive to high-energy particles. A single cosmic ray striking a transistor can flip bits of data, corrupt software, or cause permanent hardware failure. On Earth, these events are rare and manageable. On Mars, they would be constant. Spacecraft destined for deep space are equipped with radiation-hardened electronics, specially designed components that resist particle strikes. But these systems are expensive, bulky, and still far from invulnerable. A Mars colony would require vast arrays of computers for life support, navigation, communication, and industrial processes. Maintaining these systems under relentless radiation bombardment would be a Sisyphean task, with failures cascading faster than repairs could be made. Every critical system would need redundancy, and every redundancy would need shielding. The infrastructure demands spiral outward, each solution revealing 10 new problems. What makes radiation so uniquely devastating is its invisibility and inevitability. Colonists could monitor their exposure with dosimeters, track cumulative radiation, and retreat to shielded zones when levels spike. But unlike a storm that passes or a mechanical failure that can be repaired, radiation never stops. It is there in the silence of night, in the stillness of day, penetrating walls, passing through flesh, accumulating damage molecule by molecule. There is no respite, no safe season, no moment when vigilance can relax. Living on Mars would mean living under a sentence of slow, biological decay, knowing that every hour outside a shielded zone brings cellular damage that cannot be undone. Some have proposed underground colonies, entire cities carved into Martian rock, hidden beneath dozens of meters of stone. This approach would reduce radiation exposure significantly, but it introduces other profound challenges. Excavating vast underground chambers would require enormous energy and advanced machinery, all of which must first survive the radiation environment long enough to complete the work. Colonists would live in perpetual darkness, cut off from the sky, from natural light, from any connection to the surface. The psychological toll of such confinement, combined with the knowledge that even deep underground some radiation still penetrates, would be immense. And if systems fail, if life support falters, escape routes are limited. An underground colony becomes a tomb far more easily than a surface habitat ever could. No current technology offers a proven long-term solution for protecting humans from chronic radiation exposure at Martian levels. Pharmaceutical interventions, drugs designed to repair DNA damage or enhance cellular resistance, remain experimental at best. Genetic engineering to increase human radiation tolerance exists only in speculative research. Magnetic field generators, theoretical devices that could recreate Earth's protective magnetosphere on a smaller scale, would require power outputs far beyond current capabilities and remain decades away from practical implementation if they are possible at all. Every proposed solution is either unproven, prohibitively expensive, or relies on technologies that do not yet exist. The radiation problem is not a gap in our knowledge. It is a fundamental obstacle rooted in the physics of space and the biology of life. And so we return to the silent arithmetic of survival. A colony on Mars would watch its members absorb radiation day after day, month after month, knowing that the damage is irreversible. Cancer rates would climb. Cognitive decline would become the norm. Equipment would fail. Systems would degrade. Medical crises would multiply faster than limited supplies, and personnel could address them. Within months, the colony would not collapse from a single catastrophic failure, but from the slow, relentless erosion of health, capability, and morale. Radiation is not dramatic. It does not explode or announce itself. It simply takes, silently and without pause, until there is nothing left to give. To understand radiation on Mars is to confront a truth we rarely acknowledge. The universe is not indifferent to life. It is hostile to it. We exist on Earth not because life is resilient, but because our planet provides extraordinary protection. Strip away the magnetosphere, thin the atmosphere, and life becomes unsustainable. Mars is that stripped world. A planet where the forces that make space lethal operate without restraint. A colony there would not thrive in spite of radiation. It would struggle merely to delay its inevitable effects, buying time measured in months, not generations. As we move forward in our examination of why a Mars colony would collapse, radiation stands as perhaps the most insurmountable barrier. It cannot be negotiated with, worked around, or temporarily endured. It is always present, always damaging, always claiming its toll. In the silence between heartbeats, in the darkness between stars, radiation reminds us that some frontiers are not meant to be crossed, and some dreams, no matter how compelling, cannot survive the cold mathematics of physics and biology. Mars offers no escape from this silent killer, and a colony built in its shadow would be a testament not to human achievement, but to the limits of human endurance in a universe that offers no shelter. After months of survival within the colony, a new crisis begins to emerge, one that unfolds not in hours but in the slow, creeping realization that something essential is missing. Food. Not the freeze-dried rations brought from Earth, carefully calculated and portioned, but real food, grown food, the kind that can sustain a colony indefinitely. On Mars, the dream of self-sufficiency collides with a truth older than agriculture itself. Without soil, without water, without the delicate web of life that makes Earth's fields flourish, growing food becomes not just difficult but nearly impossible. The challenge is not simply to plant seeds and wait. It is to recreate an entire ecosystem in a place where none has ever existed. The settlers begin with optimism. They have greenhouses assembled from prefabricated modules, transparent domes designed to capture every photon of sunlight. They have seeds, carefully selected varieties engineered for efficiency, potatoes, wheat, soybeans, lettuce. They have nutrient solutions, growth lights, and plans meticulously designed by the brightest agricultural scientists on Earth. But within days of the first planting, the problems begin. The Martian soil, ruddy and abundant, reveals its first terrible secret. It is not soil at all, it is poison. Martian regolith, the fine dust that blankets the planet's surface, contains perchlorids, chemical compounds made of chlorine and oxygen that exist in concentrations deadly to both plants and humans. On Earth, perchlorids are rare, found in only a few arid regions, and even there they are considered contaminants. On Mars, they are everywhere. These compounds interfere with thyroid function in humans, disrupting hormones and metabolism. In plants, they inhibit growth, damage cellular structures, and accumulate in tissues, making any food grown in untreated Martian soil toxic to consume. The settlers cannot simply dig, plant, and harvest. They must first cleanse the soil, a process requiring water, heat, or chemical treatment, each method consuming resources the colony cannot afford to spare. But even if the perchlorids are removed, the soil remains fundamentally broken. Earth's soil is alive. It teems with bacteria, fungi, earthworms, and microorganisms that decompose organic matter, fix nitrogen, and create the nutrient-rich environment plants need to thrive. Martian regolith is sterile, lifeless, a mineral dust devoid of organic compounds. It contains iron, silicon, and magnesium, but it lacks nitrogen, the element plants require in abundance to build proteins and grow. On Earth, nitrogen cycles through the atmosphere, the soil, and living organisms in a continuous exchange. On Mars, nitrogen is scarce, locked away in trace amounts in the thin atmosphere or buried deep beneath the surface. Without nitrogen, plants cannot grow. Without plants, the colony cannot eat. The solution seems obvious. Import nitrogen from Earth, bring compost, bring fertilizers, bring the building blocks of life itself. But the cost is staggering. Every kilogram of material sent to Mars requires vast amounts of fuel and planning. A colony of 100 people needs tons of food each year. To grow that food requires tons of nitrogen. To transport that nitrogen requires a continuous supply chain that, if interrupted even once, means starvation. The colony cannot afford to depend on Earth forever. Yet without Earth's support they cannot grow food at all. The paradox is inescapable. Even if the soil is made fertile, the next challenge emerges from the sky, or rather the lack of it. Plants need light, not just any light, but specific wavelengths in precise intensities, sustained over hours each day. On Mars, sunlight is weaker than on Earth, filtered through a thin atmosphere and dust storms that can last for months, blocking even the dim glow that reaches the surface. The colony's greenhouses rely on artificial lighting, rows of LED arrays designed to mimic the sun's spectrum. These lights consume enormous amounts of energy, drawing power from solar panels that are themselves compromised by the very dust that covers everything on Mars. As dust accumulates on the panels, energy output drops. As energy drops, the lights dim. As the lights dim, the plants begin to die. The settlers must choose divert power from life support to save the crops, or let the crops fail and ration the remaining food. Either choice brings them closer to collapse. Water, too, becomes a silent executioner of agricultural hope. Growing food is not merely about planting seeds. It is about sustaining life through every stage of growth, and life requires water in quantities the colony cannot reliably provide. A single kilogram of wheat requires roughly 1,500 litres of water to grow from seed to harvest. Potatoes, lettuce, tomatoes all demand water in amounts that dwarf the colony's reserves. On Earth, this water comes from rain, rivers, and underground aquifers, replenished continuously by the planet's hydrological cycle. On Mars, water is locked in ice beneath the surface or bound in minerals, requiring energy and equipment to extract. Every litre used for crops is a litre taken from drinking water, from oxygen production, from cooling systems that prevent equipment from overheating. The mathematics are unforgiving. The more food the colony tries to grow, the faster their water supply dwindles. Without resupply from Earth, they are simply choosing how quickly they will die of thirst instead of starvation. But even if the soil is cleansed, the nitrogen imported, the lights powered, and the water rationed, another invisible crisis waits in the silence of the greenhouses. On Earth, food does not grow in isolation. It grows within an ecosystem. Flowers are pollinated by bees, butterflies, wind, and insects that move pollen from plant to plant, enabling reproduction and the formation of seeds and fruit. On Mars there are no insects. There is no wind strong enough to carry pollen. There is only the colonists, exhausted, overworked, and now tasked with the labour-intensive process of manual pollination. With brushes and cotton swabs, they move from flower to flower, mimicking the work of bees, hoping they transfer enough pollen to ensure a harvest. One missed flower means lost food. One mistake in timing means an entire crop fails. Agriculture, which on Earth is aided by millions of invisible workers, becomes on Mars a task measured in human hours, each one stolen from maintenance, from research, from sleep. And still, the margin for error remains non-existent. On Earth, if one field fails, another may thrive. If one harvest is poor, food can be imported from neighbouring regions or stored reserves drawn upon. On Mars, there is no neighbouring region. There are no reserves beyond what was brought from Earth. A single system malfunction, a pump failure, a contamination, a temperature fluctuation can destroy an entire crop cycle. When that happens, the colony does not go hungry for a week. They begin to starve. Resupply missions from Earth take months, even years, to plan and execute. By the time help arrives, it may find only empty habitats and silent greenhouses, monuments to ambition and miscalculation. Even if the crops grow, even if the harvest succeeds, the colonists face another slow, insidious threat: malnutrition. The crops they can grow on Mars are chosen for efficiency, not variety. Potatoes, grains, legumes, leafy greens, all high in calories, but lacking the full spectrum of nutrients the human body requires. Vitamins, minerals, amino acids, these come not from a single crop but from diversity, from fruits, vegetables, nuts, fish, and meat, from the vast array of foods that Earth provides naturally. On Mars, that diversity does not exist. The settlers eat the same meals day after day, week after week. Deficiencies begin to appear. Vitamin D, despite supplements, remains insufficient. Vitamin B12, found primarily in animal products, becomes scarce. Iron, calcium, omega-3 fatty acids all grow harder to maintain. The body begins to break down. Bones weaken. Immune systems falter. Wounds heal more slowly. The colonists are not starving in the traditional sense. They are consuming calories, but they are starving nonetheless, deprived of the nutrition their bodies need to function. And with malnutrition comes another quieter collapse, the psychological toll. Food is not merely fuel, it is comfort, culture, connection. On Earth, meals are celebrations, moments of rest and enjoyment. On Mars, meals become monotonous rituals, the same rehydrated vegetables, the same protein paste, the same flavourless grains. The settlers begin to dread eating, not because they are not hungry, but because every meal is a reminder of what they have lost. Morale erodes, depression deepens. The act of eating, once a source of pleasure, becomes a chore, another task on a list of survival requirements. The body may still receive calories, but the mind begins to starve for something more, for variety, for taste, for the simple joy of a meal shared among friends. Food production on Mars is not a single challenge. It is a cascade of interdependent systems, each one fragile, each one essential. Soil must be cleansed and enriched. Water must be extracted and conserved. Energy must be generated and distributed. Pollination must be performed by hand. Crops must be protected from failure. Nutrition must be balanced against limited variety. And morale must be maintained in the face of relentless monotony. Each link in this chain is weak. Break one, and the entire system collapses. The settlers are not farmers. They are engineers, chemists, and labourers attempting to sustain life in a place that offers none of the foundations agriculture requires. As the days stretch into months, the greenhouses stand as fragile symbols of hope and futility. Inside, a few rows of pale lettuce grow beneath humming lights. Outside, the rust-coloured plains stretch endlessly, barren and different. The settlers water their crops with hands that tremble from exhaustion, knowing that each harvest brings them closer not to self-sufficiency, but to the inevitable realization that Mars will not feed them. Not now, perhaps not ever. They are sustained only by the hope that the next resupply mission will arrive on time, that the food brought from Earth will last just a little longer, that somehow, against all odds, they will find a way to make the impossible possible. But hope, like crops, requires more than intention to grow. It requires soil, water, light, and time. And on Mars, time is the one resource running out faster than all the others. Water is not merely a resource on Mars. It is the thread that holds survival together, and that thread is thinner than most dare to imagine. Every human need traces back to water. Every breath we exhale contains it. Every meal we prepare requires it. Every plant we grow depends upon it. On Earth, water cycles through rain and rivers, through oceans and aquifers, renewing itself endlessly. On Mars, water is locked away in ice, buried beneath dust and regolith, frozen into permanence by a world that has forgotten how to flow. To access it is not a matter of drilling a well or turning on a tap. It is an industrial undertaking that demands energy, technology, and resources the colony does not yet possess. The Martian ice deposits lie hidden beneath the surface, scattered across the polar regions and certain mid-latitude zones. These underground reserves represent the colony's only significant water source, yet extracting them is far from simple. Mining ice on Mars requires heavy machinery capable of penetrating meters of frozen soil in temperatures that plunge to minus 125 degrees Fahrenheit. Each excavation must be powered by energy drawn from solar panels struggling under a dimmer sun, or nuclear reactors whose fuel is limited and irreplaceable. The ice, once extracted, must be melted, purified and transported to habitats through insulated pipelines that themselves consume energy to prevent refreezing. This is not water collection, this is water manufacturing, and every litre comes at a cost measured in kilowatts, and machine hours the colony can barely afford. But extraction is only the beginning. The ice beneath the Martian surface is not pure. It is laced with perchlorates, toxic salts that permeate the Martian regolith and render the water undrinkable without extensive chemical treatment. Perchlorates disrupt thyroid function in humans, accumulate in the body, and contaminate crops if introduced into agricultural systems. Removing them requires reverse osmosis, ion exchange filtration, or chemical neutralization, processes that demand specialized equipment, replacement filters, and again, energy. A single failure in the purification chain could release contaminated water into the colony's supply, poisoning the very resource upon which all life depends. On Mars, water is not merely scarce, it is dangerous until proven otherwise. Even if the colony successfully extracts and purifies water, the challenge of maintaining it begins. On Earth, water cycles naturally. It evaporates, condenses, and returns. On Mars, within the sealed environment of a habitat, every drop of water must be captured, recycled, and reused with near-perfect efficiency. The International Space Station has pioneered closed-loop water recycling systems capable of recovering roughly 93% of water from urine, sweat, and humidity. That remaining 7% loss, acceptable in low Earth orbit where resupply missions arrive regularly, becomes catastrophic on Mars. A colony of 100 people requires approximately 100 litres of water per person per day for drinking, hygiene, food preparation and agriculture. That is 10,000 litres daily. Losing even 5% to inefficiency means 500 litres vanish each day, 182,500 litres per year. There is no resupply mission. There is no rain to replenish what is lost. The math is unforgiving. Achieving near-perfect water recycling is a goal no human system has ever accomplished for extended periods. The ISS loses water constantly, even with the most advanced technology humanity has developed. Seals degrade, filters clog, humidity condenses in places it should not, forming ice in ventilation systems or pooling in hidden corners where it evaporates into the cabin atmosphere and escapes through air exchange systems. On Mars, these inefficiencies compound. The habitat's environmental control systems must walk a razor's edge, extracting moisture from the air to prevent excessive humidity, while ensuring that extracted water is captured and returned to the supply. If humidity rises too high, condensation forms on walls, equipment, and electronics, corroding circuits and fostering mold growth in a sealed environment where contamination spreads rapidly. If humidity drops too low, colonists suffer respiratory problems and water evaporates from every exposed surface, vanishing into the air and eventually lost through inevitable atmospheric leaks. Every human activity on Mars becomes a water accounting problem. A single shower consumes 40 litres of water that must be filtered, purified, and returned to use. A toilet flushes water that must be separated from waste, sterilized, and recycled. Cooking evaporates water into steam that must be captured before it escapes. Laundry, though infrequent, demands water that emerges contaminated with detergents and must be chemically treated before reintroduction. Even breathing contributes. Each colonist exhales roughly 1 litre of water vapour per day, moisture that environmental systems must recover or lose forever. The entire colony operates as a desperate Xunhuan. constantly chasing molecules of water through an endless series of transformations, knowing that each inefficiency brings them closer to dehydration. Water purification system failures are not minor inconveniences, they are existential threats. A single malfunction, a clogged filter unnoticed for too long, a chemical imbalance in the treatment process, a bacterial contamination introduced through a failing seal, can compromise the entire water supply within days. Unlike on Earth, where contaminated water can be dumped and replaced, on Mars there is no replacement. The colony's entire water reserve, perhaps stored in tanks holding a few weeks' supply at most, represents the sum total of available water. If contamination spreads through the system, every litre becomes suspect. Boiling can kill bacteria but requires energy and does nothing against chemical contaminants. Filtration systems, already strained by continuous use, may lack the capacity to process the entire supply quickly enough. The colonists face a cruel choice: drink potentially poisoned water or ration the remaining safe supply so severely that dehydration becomes inevitable. Manufacturing water from its chemical components offers a theoretical solution, but one that collapses under practical scrutiny. Water is H2O, two hydrogen atoms bonded to one oxygen atom. Mars has carbon dioxide in abundance, which can be split into oxygen and carbon monoxide through electrolysis. Hydrogen, however, is rare on Mars. It can be extracted from the soil in trace amounts, or transported from Earth at prohibitive cost. Even if hydrogen is available, producing water through chemical synthesis requires electrolysis, heating, and recombination, processes that consume staggering amounts of energy. Producing a single litre of water through synthesis might demand several kilowatt-hours of electricity, energy that could otherwise power life support, heating, or communications. Scaling this process to produce thousands of litres daily becomes energy prohibitive. The colony cannot manufacture its way out of water scarcity. It can only recycle what it has and hope the systems never fail. Underground ice, the great hope of Martian colonization, presents yet another challenge: accessibility. The most substantial ice deposits lie in the polar regions, where temperatures are coldest and solar energy weakest. Establishing mining operations there demands transporting heavy equipment across hundreds or thousands of kilometers of rough terrain, building remote facilities, and maintaining supply lines across distances that strain the colony's limited vehicles and fuel reserves. Mid-latitude ice deposits exist closer to proposed habitats, but they lie buried beneath layers of regolith that must be excavated, sifted, and processed. Every kilogram of ice extracted comes with kilograms of dirt that must be moved, heated, and separated. This is not a water source. This is an industrial mining operation conducted on a planet where every machine failure, every broken drill bit, every malfunctioning heater threatens the colony's survival. Leaks represent the silent death of water security. In the sealed environment of a Mars habitat, even microscopic cracks in pipes, tanks, or airlocks allow water vapor to escape into the thin Martian atmosphere, where it freezes instantly and is lost forever. Detecting these leaks requires constant monitoring, pressure sensors, and humidity meters sensitive enough to notice fractional changes. Repairing leaks demands shutting down sections of the water system, draining pipes, and performing maintenance in bulky pressurized suits within cramped spaces. Each repair consumes time, labor, and water reserves that the colony cannot afford to set aside. Yet without repairs, the leaks persist, slowly bleeding the colony's water supply into the void. The colonists exist in a state of perpetual triage, patching leaks as they appear, knowing that others are forming elsewhere. unseen and undetected until they become critical. Water reserves, the buffer against system failure, represent a luxury Mars cannot provide. On Earth, municipalities maintain reservoirs holding weeks or months of supply. On Mars, every kilogram of stored water is a kilogram that must be transported, heated to prevent freezing, and protected from contamination. Storage tanks themselves are heavy, require pressurization to prevent boiling in the low-pressure environment, and occupy space within habitats already stretched to maximum capacity. A colony might maintain a reserve of a few days' water, perhaps a week if they sacrifice space for other critical systems. Beyond that, storage becomes impractical. The colony operates on a just-in-time water system, where daily consumption is met by daily recycling. There is no cushion. There is no margin for error. A single breakdown in the recycling process means the reserve is consumed in days, and after that there is nothing. Agriculture, essential for long-term survival, compounds the water crisis exponentially. Growing food hydroponically or in Martian soil enriched with nutrients requires constant irrigation. Plants transpire water through their leaves, moisture that must be captured by environmental systems and returned to the reservoir. Evaporation from soil surfaces, leakage from irrigation lines, and absorption into plant biomass all represent water that is temporarily removed from circulation. If crops fail, the water invested in them is lost. If crops succeed, they produce food but lock water within their tissues until consumed, a delay in the recycling process that strains the system. The colony faces a paradox. They cannot survive without growing food, but growing food consumes water they cannot spare. Even the simplest human comforts become unattainable luxuries. Showering transforms from daily routine to rare indulgence, rationed to perhaps once per week to conserve water. Laundry is minimized. Colonists wear the same clothes for days, weeks, until the fabric stiffens with salt and sweat. Cooking is simplified to methods that minimize water use. Fresh water for drinking is measured in rations. Washing hands becomes a calculated decision. Every act that involves water is weighed against the colony's dwindling reserves and the fragile recycling systems struggling to keep pace. The psychological toll of this deprivation, the constant awareness that water is not a given but a privilege earned through relentless mechanical efficiency, erodes morale as surely as thirst erodes the body. The water crisis on Mars is not a problem with a single solution. It is a web of interconnected failures waiting to happen. Extraction demands energy. Purification demands equipment. Recycling demands near perfection. Storage demands space. Contamination demands immediate response. Leaks demand constant vigilance. Every system depends on every other, and the failure of one cascades through the rest. Water, the most basic requirement of life, becomes the most fragile element of Martian existence. The colony does not merely need water, it needs miracles of engineering repeated daily, flawlessly, indefinitely. And in the cold dust of Mars, miracles are in short supply. As we consider the thin line between survival and collapse, we begin to see water not as a substance, but as a clock. Every drop recycled is another hour of life. Every drop lost is time stolen from the future. And on Mars, time does not wait. On Earth, when the power goes out, we light candles, we wait. We know the lights will return. On Mars, when the power fails, there are no second chances. There is no backup grid, no neighbouring city to call, no repair crew arriving within hours. On Mars, electricity is not a convenience. It is the single thread holding life itself together. Without it, oxygen production stops. Water freezing systems fail. Heat dissipates into the void. Within hours, a colony transitions from functioning habitat to frozen tomb. The power grid on Mars cannot fail, and yet it is designed within an environment that makes failure inevitable. The foundation of Martian energy is solar power. Panels stretching across the rusty surface, tilted toward a sun that appears half the size it does from Earth. But here is the uncomfortable truth that promotional videos rarely mention. Mars receives only 43% of the sunlight that reaches Earth. The inverse square law of light intensity is not a suggestion, it is absolute. At Mars's distance from the Sun, approximately 142 million miles, every square metre of solar panel collects less than half the energy it would on Earth. This means that to generate the same power, a Martian colony needs more than twice the solar infrastructure. More panels, more weight, more complexity. And complexity in an environment as hostile as Mars is the enemy of survival. Even if engineers design expansive solar arrays capable of compensating for reduced sunlight, they face a challenge far more insidious: dust. Mars is not a world of gentle breezes and clear skies. It is a planet perpetually cloaked in fine, abrasive particles that cling to every surface with electrostatic persistence. When dust settles on solar panels, it does not blow away. It accumulates. Studies of Mars rovers have shown that dust accumulation can reduce solar panel efficiency by 40% or more over the course of weeks. On Earth, rain cleans panels naturally. On Mars there is no rain. There is only dust settling like a shroud, smothering the very technology meant to sustain life. During global dust storms, events that can last for months and engulf the entire planet, sunlight is reduced to a dim twilight. The sky turns ochre. The sun becomes a faint disk barely visible through the haze. Solar panels produce almost nothing. NASA's Opportunity rover, one of the most resilient machines ever sent to another world, survived dust storm after dust storm for over 14 years. But in 2018, a planetary dust storm finally silenced it. The panels could no longer gather enough light. The batteries drained. The rover went dark, never to wake again. If a solar-powered rover designed for minimal energy consumption cannot survive a dust storm, how can a colony demanding continuous power for life support, heating, water processing, and food production? The cold truth is this: solar power on Mars is fragile, it is vulnerable, and it is insufficient for long-term human survival. So we turn to batteries, massive energy storage systems designed to hold power during the long Martian nights, which last nearly 12.5 hours, or during dust storms when solar generation ceases entirely. But batteries are not eternal reservoirs. They degrade, and on Mars they degrade rapidly. Martian nights plunge temperatures to negative 80 degrees Fahrenheit or lower. Lithium-ion batteries, the most common energy storage technology, suffer catastrophic capacity loss in extreme cold. Chemical reactions slow. Internal resistance increases. The battery that could once power life support for 12 hours may, after months of thermal cycling, provide only 6, then 4, then none at all. Battery degradation is not a hypothetical problem. It is a certainty. Every charge-discharge cycle wears down the electrodes. Every freeze contracts the materials. Every thaw expands them again. Cracks form. Efficiency plummets. And there is no factory on Mars producing replacement batteries. No supply chain. No delivery truck. Once the batteries fail, they are dead weight. Expensive, useless, and irreplaceable. The colony cannot rely on solar and batteries alone, so engineers propose nuclear reactors, small modular fission reactors capable of producing steady, reliable power regardless of dust storms, day-night cycles, or seasons. Nuclear energy seems like the solution. It is dense, it is continuous, it does not depend on sunlight. But nuclear reactors are not simple machines. They are extraordinarily complex systems requiring fuel, cooling, maintenance, and waste management. And on Mars, every one of those requirements becomes a potential point of catastrophic failure. A nuclear reactor generates heat through controlled fission. That heat must be converted into electricity, typically through steam turbines or thermoelectric generators. Both methods require cooling systems to dissipate waste heat. On Earth, reactors use water or air for cooling. On Mars, there is no liquid water. The atmosphere is too thin to provide meaningful air cooling. Engineers would need to design entirely new cooling systems, perhaps using subsurface ice or radiative cooling panels. But these systems add mass, complexity, and risk. If a cooling system fails, the reactor overheats. If it overheats, it may shut down automatically to prevent meltdown. And if it shuts down, the colony loses power instantly. Nuclear fuel is another problem. Uranium or plutonium must be transported from Earth, an extraordinarily expensive and politically sensitive endeavour. A small reactor might operate for years on a single fuel load, but eventually it will need refueling. On Earth, refueling is performed by trained technicians in controlled environments with specialized equipment. On Mars, it would have to be done by colonists in bulky spacesuits, under extreme radiation exposure, with limited tools. One mistake, one dropped fuel rod, one breach in containment, and the consequences are irreversible. And then there is maintenance. Mechanical systems fail, seals degrade, electronics malfunction. On Earth, if a reactor component fails, replacement parts can be manufactured or shipped within days. On Mars, replacement parts must either be pre-positioned, adding to cargo weight, or 3D printed on site, assuming the colony has the materials and technical expertise. If a critical component fails and no replacement exists, the reactor goes offline, permanently. The terrifying reality is that every system on Mars runs on electricity. Life support systems extract oxygen from the atmosphere and filter carbon dioxide. Processes that require continuous power. Water extraction from subsurface ice demands heating elements to melt the ice and pumps to move the water. Food production under artificial grow lights consumes enormous amounts of energy. Temperature regulation, whether heating during the frigid nights or cooling during the day, drains power constantly. Communications with Earth, essential for guidance and morale, require energy. Every single function necessary for survival is electrical. This creates a cascading failure scenario. If the power grid fails, oxygen generation stops first. The colony has perhaps hours of reserve oxygen in tanks, maybe a day if consumption is minimized. But eventually carbon dioxide levels rise. Colonists begin to feel drowsy, confused, then unconscious. Meanwhile, heating systems fail. Temperatures inside the habitat plummet. Water in pipes freezes and bursts. Electronics frost over. Grow lights go dark. Plants begin to die. Within 24 hours of total power loss, the habitat becomes uninhabitable. Within 48 hours, it is a frozen graveyard. There is no realistic backup. On Earth, if a city loses power, diesel generators kick in. Emergency services arrive. But Mars has no emergency services. A backup diesel generator requires fuel, which must be shipped from Earth at astronomical cost. It requires oxygen for combustion, which is scarce. Solar panels cannot provide backup during a dust storm because they are already non-functional. batteries cannot provide backup if they are already depleted or degraded. A second nuclear reactor could theoretically serve as redundancy, but that doubles the cost, weight, and complexity of the mission, making it financially and logistically prohibitive. Energy on Mars is not just about generating power, it is about generating enough power, continuously, reliably, and indefinitely. And the math is unforgiving. Studies estimate that a small Mars colony of just 10 people would require between 40 and 50 kilowatts of continuous power. That is equivalent to running 4 or 5 average American homes, but under conditions exponentially more hostile. Solar panels must be oversized to account for dust and distance from the sun. Batteries must be oversized to account for degradation and long nights. Nuclear reactors must be oversized to account for inefficiencies and cooling losses. The energy infrastructure alone could constitute the majority of a mission's mass budget, leaving less room for food, water, spare parts, and human cargo. And then the dust storms return. Not small localized storms, but planet-wide tempests that blot out the sun for weeks or months. During the 2018 global dust storm, Mars became nearly invisible from space, shrouded entirely in particulate matter. Solar power generation dropped to near zero across the planet. If a colony were present during such an event, it would have to rely entirely on stored energy. Batteries would drain day by day. Rationing would begin. Non-essential systems would be shut down. Then essential systems would be cycled. Grow lights off, heating reduced, oxygen production minimized. The colony would enter a state of emergency hibernation, waiting for the storm to pass, knowing that every hour brings them closer to the point of no return. The psychological toll of living under such energy scarcity is immeasurable. Imagine knowing that the lights above you, the warmth around you, the air you breathe, all depend on a single fragile grid. Imagine hearing the hum of the reactor and wondering, what if it stops? Imagine watching the dust settle on the solar panels outside and calculating day by day how much power is left. This is not the frontier spirit of exploration. This is survival under perpetual siege. The energy deficiency on Mars is not a technical problem waiting for a clever solution. It is a fundamental constraint imposed by physics, distance, and environment. Mars is too far from the sun. Its atmosphere is too thin. Its dust is too persistent. Its cold is too extreme. Every energy generation method we possess is either insufficient, unreliable, or unsustainable in the Martian context. And because every system necessary for life depends on continuous electricity, the failure of the power grid is not merely an inconvenience, it is extinction. We dream of cities on Mars powered by sleek solar arrays and humming reactors, but the reality is far grimmer. The power grid on Mars must never fail, and yet in an environment designed by nature to corrode, freeze and smother, failure is not a possibility, it is a certainty. The only question is when. Of all the challenges a Mars colony must face, none are as complex and unpredictable as the human element itself. Technology can be engineered, structures can be reinforced, and systems can be designed with redundancy. But the human mind, the human body, and the fragile bonds that hold small groups together, these cannot be solved with better materials or clever design. They are variables that shift, evolve, and sometimes break under conditions for which evolution has not prepared us. To understand why a Mars colony would collapse, we must turn our gaze inward, to the darkest and most vulnerable frontier of all, the psychology and physiology of isolation, confinement, and irreversible distance from home. Imagine waking each morning inside a pressurized habitat no larger than a small house, surrounded by the same handful of faces you've seen every day for months, perhaps years. Outside the transparent dome, the rust-colored wasteland stretches endlessly in every direction. There are no forests to wander through, no oceans to gaze upon, no cities bustling with strangers. There is only silence, dust, and the knowledge that you're 140 million miles from the nearest human being who is not standing beside you. This is not a camping trip. This is not an adventure with an end date. This is permanence, or something disturbingly close to it. And the human mind evolved to thrive in rich, dynamic environments filled with novelty and social complexity begins to falter under such conditions. Extreme isolation and confinement are not new experiences for humanity. Antarctic research stations, submarines, and space stations have taught us much about what happens when people are sealed inside small environments for extended periods. Depression becomes common, even among those screened for psychological resilience. Anxiety intensifies as the days blur together, each one indistinguishable from the last. Interpersonal conflicts arise over trivial matters, a misplaced tool, a repeated phrase, the way someone chews their food. These are not signs of weakness. They are the inevitable result of removing the psychological buffers that human societies depend on. Personal space, privacy, the ability to walk away, the presence of a broader social network that absorbs tension and provides perspective. On Mars, these buffers do not exist. The colony is the world. There is no stepping outside for fresh air, no visiting a friend in another town, no anonymous crowds to disappear into when frustration mounts. Every disagreement is magnified because there is nowhere to escape. Every personality clash becomes a chronic stressor because the same people must work together, eat together, sleep mere walls apart day after day, indefinitely. Studies of isolated groups reveal a disturbing pattern. Even the most cooperative individuals begin to form factions. Trust erodes. Communication breaks down. In some cases, violence emerges, not because the individuals are violent by nature, but because the environment strips away the social structures that normally prevent conflict from escalating. And unlike Earth, where help can arrive, where mediation is possible, where individuals can leave toxic situations, a Mars colony offers no such options. There is no authority to appeal to, no social services, no ability to transfer to another base. The group must function, or it will die. The pressure of that reality alone is enough to warp decision-making, intensify paranoia, and erode the fragile trust that keeps any community functional. A single unresolved conflict, a single breakdown in cooperation, can cascade through the entire colony, rendering it incapable of performing the coordinated tasks necessary for survival. But the psychological toll is only part of the story. The human body too begins to fail in ways that are subtle at first, then catastrophic. Bone density loss is one of the most well-documented effects of living in low-gravity environments. On the International Space Station, astronauts lose approximately 1 to 2% of their bone mass per month, even with rigorous daily exercise. Mars, with its gravity only 38% that of Earth, slows this process somewhat but does not stop it. Over months and years, bones become brittle, hips weaken, spines compress. A fall that would result in a bruise on Earth could shatter a femur on Mars, and unlike on Earth, there is no hospital, no orthopedic surgeon, no rehabilitation centre. A broken bone becomes a permanent disability, and the injured colonist becomes a burden the group can ill afford. Muscle atrophy follows a similar trajectory. Despite exercise regimens, despite resistance training, the body adapts to the reduced gravitational load by shedding muscle tissue it no longer needs. Strength fades, endurance diminishes. Tasks that were once routine become exhausting. The colonists grow weaker with each passing month, and there is no way to reverse the process without returning to Earth. A return that, for most, will never come. Perhaps even more insidious is the effect on vision. Studies of astronauts who have spent extended periods in space reveal a troubling pattern. Intracranial pressure increases due to fluid shifts in the body, causing the eyeball to flatten and the optic nerve to swell. The result is vision degradation, blurred sight, difficulty focusing, sometimes permanent damage. On Mars, where precise manual work is necessary to repair life support systems, to conduct scientific research, to operate machinery, loss of vision is not a minor inconvenience. It is a death sentence, delivered slowly, one blurred image at a time. And then there are the medical emergencies that cannot be anticipated but are statistically inevitable. A burst appendix, a severe tooth infection, a deep laceration, a cardiac event. On Earth, these are survivable with prompt medical intervention. On Mars, they are fatal. There is no trauma surgeon. There is no anesthesia for complex procedures. There is no dental specialist to perform a root canal or extract an impacted molar. Medical knowledge, even extensive training, cannot replace the tools, the sterile environments, the blood supplies, and the surgical expertise required for even moderately complex procedures. A colonist suffering a serious medical emergency will die, and the rest of the group will be forced to watch, powerless, as their companion succumbs to an injury or illness that would be routine to treat on Earth. The psychological impact of witnessing such a death cannot be overstated. It is one thing to accept intellectually that Mars is dangerous. It is another to hold the hand of a colleague as they slowly fade, knowing that there is nothing you can do, that no help is coming, that this will not be the last time. Morale, already strained by isolation and physical decline, collapses. The death of one becomes the unspoken dread of all. Every headache becomes a potential aneurysm. Every stomachache becomes appendicitis. The colony begins to live in a state of constant low-grade terror, waiting for the next catastrophe that no one can prevent. There is also the absence of an escape option, a psychological safety valve that humans depend on more than they realize. On Earth, even in the most difficult circumstances, there is always the possibility of leaving. A person can quit a job, move to a new city, end a relationship, start over. This possibility, even if never acted upon, provides a sense of control, a belief that one's fate is not entirely fixed. On Mars, that option does not exist. There is no quitting. There is no moving away. There is no starting over. The colony is a cage, and the knowledge that it is inescapable creates a form of existential dread that gnaws at the mind day after day until even the most resilient individuals begin to crack. Even the passage of time on Mars works against human psychology. A Martian day, or sol, lasts 24 hours and 39 minutes, just slightly longer than an Earth day. This may seem trivial, but the human circadian rhythm is finely tuned to a 24-hour cycle. Studies have shown that even small mismatches between environmental time and biological time lead to chronic sleep disorders, impaired cognitive function, and increased rates of depression. On Mars, every day drifts slightly out of sync with the body's internal clock. Sleep becomes fragmented, alertness declines, decision-making suffers. Over months, the cumulative effect is profound. a colony of sleep-deprived, cognitively impaired individuals attempting to manage systems where a single mistake can be fatal. And then there is the social collapse that follows inevitably from all of these factors. A group that is isolated, physically deteriorating, psychologically strained and deprived of sleep will not function as a cohesive unit for long. Leadership structures break down, resentments fester, cooperation gives way to self-preservation. In the worst cases, violence emerges, not as an act of madness, but as a rational response to unbearable conditions. A person who feels trapped, who sees no future, who has lost trust in their companions may lash out. And in an environment where every individual is essential to survival, the loss of even one person to violence, exile, or suicide can trigger a cascading collapse from which the colony cannot recover. The human factor is not a supplementary concern. It is the central challenge, the weak link that no amount of engineering can reinforce. We can build habitats that resist radiation. We can design greenhouses that recycle nutrients. We can generate power from the sun and extract water from the soil, but we cannot redesign the human mind and body to thrive in conditions of extreme isolation, low gravity, and existential danger. We are shaped by millions of years of evolution on a planet with breathable air, abundant water, stable gravity, and rich social environments. Mars offers none of these. To send humans to Mars without acknowledging these realities is not optimism. It is delusion. The collapse of a Mars colony would not begin with a technical failure. It would begin with a person who can no longer sleep, whose bones ache, whose vision is failing, who looks at their companions and sees not, allies but strangers they no longer trust. It would begin with the quiet unravelling of hope, the slow erosion of purpose, the creeping realization that survival is not the same as living. And in the end, the colony would not fall to radiation or starvation, but to something far more human: despair, conflict, and the simple, unavoidable truth that we were never meant to be so far from home. As we stand at the edge of this imagined Martian colony, watching it crumble in the thin, toxic air, we are confronted not with a single failure, but with a cascade of interconnected collapses. Each system we have explored, atmosphere, radiation shielding, food production, water extraction, energy generation, human psychology, does not exist in isolation. They form a web of dependencies so intricate that the failure of one accelerates the failure of all others. When the power grid fails, the greenhouse loses heat. When the greenhouse fails, morale collapses. When morale collapses, maintenance is neglected. When maintenance is neglected, life support systems begin to fail. This is not a colony. It is a house of cards built on another planet, and Mars is an unforgiving wind. The sobering truth is this: Mars colonization is not impossible, but it is not imminent. What separates our current capabilities from a sustainable Martian settlement is not measured in years, but in decades, perhaps generations. We do not yet possess the technology to overcome these challenges simultaneously. We have prototypes, concepts, and promising experiments. But a prototype tested on Earth is not the same as a system that must function flawlessly, continuously, for years in an environment actively hostile to human life. Current proposals, no matter how ambitious or well-funded, vastly underestimate the complexity of what lies ahead. They present timelines measured in decades when the reality may require a century. They promise self-sufficiency within years when true independence from Earth may take lifetimes to achieve. This is not pessimism. It is respect for the magnitude of the challenge. It is acknowledgement that Mars will not yield to our desires, only to our preparation. The red planet does not care about our deadlines, our funding cycles, or our dreams of becoming a multi-planetary species. It simply exists, silent and patient, waiting for humanity to develop not just the technology, but the wisdom to survive there. And yet, this conclusion is not an ending. It is a redirection. The path forward requires honesty about where we truly stand. It demands investment not in grand missions planned for the next decade, but in fundamental research that may take 50 years to bear fruit. We need breakthroughs in closed-loop life support, in radiation shielding, in autonomous robotics, in human psychology under extreme isolation. We need to learn not just how to survive on Mars, but how to build systems so robust, so redundant, so intelligently designed that they can sustain human life without constant intervention from Earth. The dream of Mars is not dead. It is simply further than we thought, and perhaps that is as it should be. The greatest achievements in human history were not rushed. They were earned through patience, through failure, through the slow accumulation of knowledge across generations. As we close this journey through the science of Martian collapse, we are reminded that the universe does not grant us easy victories, but it does reward persistence, ingenuity, and respect for the laws that govern all worlds, Earth and Mars alike. If this exploration has challenged your perspective, sparked your curiosity, or helped you drift towards sleep while pondering the cosmos, consider leaving a like and letting us know in the comments where in the world, or perhaps which world, you're listening from. Subscribe to continue this journey through the science that shapes our dreams and defines our limits. The path to Mars is long, far longer than most imagine, but humanity has always been a species that looks upward, that reaches beyond its grasp. One day, perhaps, we will stand on Martian soil not as visitors, but as inhabitants. That day will come not through haste, but through wisdom, not through optimism alone, but through the patient, methodical application of science, time, and the unyielding human spirit that refuses to accept impossibility as final.